about some solar panels and then going out in the world and just building them and making everything powered by renewable energy. Well, when I first got into there, about with my first term, I realized that the knowledge that I had was not enough. I didn't have the basics of anything, the fundamentals for any type of electronics that I even had the process of thinking about. So today, my project is a little bit of automation, a little bit of renewable energy brought together to create a watering sensor that is used, sorry, I gotta move this over, a simple to use sensor that reminds you to water your plants. So I'm gonna start by talking a little bit about my hardware, the pieces that I use to bring my project together. So the first piece that I am going to talk about today is my blink board. The blink board is a 10-bit system, has a voltage range of 0 to 3.3 volts, has a microcontroller, an ESP8266 Wi-Fi enabled microcontroller that enables me to communicate with my board and it communicates with me from anywhere in the world. It has an onboard FTDI to reprogram in different languages such as Arduino, Scratch, and Python. It comes with a 32 megabit serial flash memory that provides storage solutions because of the limited space and pins and power. It has large pads to easily connect alligator clips, or right behind each one of the alligator clip pads, there is a small metal circle to wire in, solder in wires. The main pin that I'll be using on my blink board is my ADC pin, which connects to my soil moisture sensor, which is a 3-pin VCC ground and signal. The signal pin is what connects up to my ADC. It has large probes that act as variable resistors. They have a gold finish on them to protect them from constantly being in moist environments. So the way that this sensor works is when the soil is wet, there is a more conductivity in the soil, resulting in a lower resistance and a higher signal or voltage out. And as the soil dries out, there is, sorry about this, I gotta move this again. When the soil dries out, the resistance is greater, resulting in a lower voltage out. So this all works together with successive approximation. That is the method of ADC that my blink board uses. A successive approximation ADC is a type of analog to digital converter that converts analog waveform into a discrete digital representation using a binary search through all possible quantization levels before finally converging upon a digital output for each conversion. The successive approximation register is initialized so that the most significant bit is equal to a digital 1. The code is fed into a digital analog converter, which then supplies the analog equivalent of this digital code, V reference, into the comparator circuit for comparison with the sampled input voltage. If this analog voltage exceeds Vn, then the comparator causes the SAR to reset this bit to 0. Otherwise, the bit is left as a 1. The next bit is set to 1, and the same test is done. Continue in this binary search until every bit in the SAR has been tested. The resulting code is a digital approximation of the sampled input voltage and is finally outputted by the successive approximation register at the end of the conversion. So this schematic is a successive approximation circuit. The analog input comes from my sensor. The reference voltage is the voltage from the chip, the 3.3 volts. So every time the sensor sends in a reading, it compares it to that reference voltage and sends it into the comparator. Now, if once it goes through all the actual bits, the most significant bit to the least significant bit, it'll output a digital representation of the analog value. So this is an example of successive approximation. It's kind of long-winded at this part, but the way it goes is the moisture threshold, which is set by me, is a 10-bit scale from 0 to 1023. 705 happens to be the range about that I did test through several days after I got my equipment all set up with my plants that shows me what the moisture content in my plant is when I want to water. So 705 is the number that I came up with. So it starts off with the most significant bit, or the 3.3 volts, 1023, and it runs through a process asking the sensor questions. So first, out of the DAC into the comparator comes a 1023, the most significant bit. It asks the sensor, are you equivalent to the 1023? The answer is no, so you put a 0 in that column and you move on to your next bit. So the sensor asks, are you equivalent to 512? This one gives you yes, so you put a 1 in the column and move on to the next bit. Now, since there's a 1 in the 512 column, you add the 512 and the 256, and it gives you 768, and it asks the sensor again, are you equivalent to 768? The answer is no, so you get a 0, it resets that column, and you move over to the next bit. So the 1 from the 512 and now 128 equals 640, and the sensor does it again. It asks the question, are you equivalent to 640? The answer is yes. You get a 1 in the column, you move over to the next bit. It runs through this process until it gets to the least significant bit, and then your ones add up to be your digital representation and your successive approximated value of 705. So that's how those two pieces come together to give me my sensor readings and to communicate with me, letting me know that my plants need to be watered. So my blink board and my project is powered through renewable energy. Now, I use a single cell 1000 milliamp hour LiPo battery and a 3.5 watt solar panel that runs through a SparkFun Sunny Buddy to make sure the battery doesn't get overcharged, and that powers my system. So my solar panel is a 7.2 volt, 3.5 watt panel that has a 450 milliamp charge rate. The panel dimensions are 4 inches by 8 inches, and it has a 3.5 millimeter jack pre-installed. The Sunny Buddy is ran with an LT3652 monolithic step-down battery charger. It comes with the standard charge rate of 450 milliamps, but has the ability for JP1 to be unsoldered and JP2 to be soldered to change the voltage divider bias to allow for a more of a charge current to 550 milliamps. It comes pre-installed with a 3.5 millimeter barrel jack for plugging directly in your solar panels, or 2 spots where you can solder in additional solar panels. On the other side, where the load is, you can solder in pins so you can actual screw down your wires, or you can solder in your load. It has a 2-pin JST PN connector installed to hook up to your single cell LiPo batteries, and the input voltage has a max of 20 volts coming from your solar panels. This Sunny Buddy is designed specifically to recharge single cell LiPo batteries. So the battery charger monitors the current flowing into the battery and limits it to some set value chosen to prevent damage to the battery. As an ideal battery charger will provide as much current to the battery as it is capable of drawing from its own power supply, but no more than the battery can handle. So the batteries that I used are lithium-ion batteries, 3.7 volts. I bought several of them, but landed with the 1000 milliamp hour because it lasts for about 4 days running my project. And with the 450 milliamp charge, it takes just over 2 hours for the solar panels to fully recharge my batteries. Next, I'm going to speak a little bit about the software with my project, the Blink app, the server, and my libraries. The Blink app is an hardware IoT platform that allows you to interface with your project via widgets. The widgets are graphical programming widgets where you just pull onto your playfield, and each widget to the right of the screen where the I drop-down menu is, there is the ability to, it gives you an editable code that allows you to play with the values, the ranges, the names, things like that are pre-programmed for each widget. Now, the app does and is compatible with different languages such as Arduino, Scratch, Python, Raspberry Pi. It has lots of boards that it's compatible with as well, not just the Blink board, but also the Red board, the Arduino Uno, many other applications that this can be used for. Now, the Blink board was developed with sensors in mind. So it has low power, things like that. It doesn't take a lot to work, and it is compatible with a lot of other platforms. And it's an open source server, which allows for the communication between your hardware and your smart device. There is no laptop required. The libraries enable communication between the server and processes all the incoming and outgoing commands. Now, the widgets that I use for my project are just few. Now, the first one was a value widget, which is connected to my ADC. This is where the values from my sensor come into my app. Once it gets into the app, it is linked to a threshold, which is a slider widget, which allows it to a 10-bit scale from 0 to 1023. This allows me to monitor my readings of my moisture and then set it to the desired watering content that I want. The next widget that I used was a Twitter widget, the Twitter widget, I've never used Twitter before, but for this project, I built an account to link it up. The app gives you the ability for push notifications, email notifications, text notifications if you'd like, or Twitter. So I chose Twitter just because I thought it was neat. I went with that and learned about it, set up an account, and I connected my Twitter account to it. And the next widget I used was another slider widget for the tweet rate. Now I set this one up from a 5-minute scale to a 60-minute scale, so I can get a tweet every 5 minutes or 60 minutes, depending once it hits that rate when it needs to be watered. The last widget I put in was a terminal widget. The terminal is just like on Linux or any other system that you've seen. This just allows you to input code and then change the programming within the app that way. It is able to actually provision your Blink board to make it to where you can get rid of all the pre-programmed graphical programming through the widgets and actually program it through Arduino Scratch, the Python, or any of the other languages. So the terminal app, like I said, is compatible with Arduino Scratch, Raspberry Pi, and Python. I was going to see, and I'm going to try to link in here real quick and get you to let me in with my phone, and I'll show you guys that app. One second, please. There we go. So now I'm going to go ahead and share my screen here. Sorry about the wait. All right, here we go. So this is my actual project. You have your moisture threshold, your moisture content where it reads the actual value. I'm going to go ahead and remove my sensor. So it happens pretty quick. You can actually see it happen. You see it drop down to 54 already. So that right there. Now when I put it back in the soil, you'll watch the content move back up. Now the moisture threshold, you can change the value. I have it set to 1023 right now, just so it sends the messages through right away. My tweet rate is set to a minimum, and I have it set to what it reads to me. Let's see if it'll actually open my Twitter here. And as you can see, the first one up top, it'll say, hello, ET241, please water me, I'm thirsty, with the soil reading. Alrighty, so my next steps are, I plan on exploring new boards like the Arduino Uno, revisiting some of the old boards like the Red board, and I plan on playing with some different sensors and ADC abilities that these boards have. I want to automate gardening. I want to build sensors for monitoring temperature and humidity levels, sensors for monitoring pH levels and parts per million for feeding, timers and solenoids to run watering pumps. I want to explore boards that have the capabilities of running all these sensors at once. I plan on incorporating renewable energy techniques to power these projects. My end goal is to design a system that can run on its own with little human interaction after the initial setup and continue to run automated until finished. So I want to thank everybody for listening to my presentation, and I'd be happy to answer any questions that anyone has.
Hey, thank Richard. You.
That's pretty cool.
I do have a question for you. An application I've always thought about would make a good one is that, you know, all those watering pots downtown for the flowers?
Yes.
So one of the things I thought this would make a nice application if you had a solar powered, if you can run everything in solar, yep. Have a reservoir in the pot, so two guys don't have to go by in a city rig every day and water the plants. They can be self-watering and just fill up the reservoir occasionally.
Yeah.
So it announced to somebody, hey, reservoir number 26 needs to be filled. You know, that kind of stuff.
Yep, that's exactly the kind of thing that I want to get into.
Yeah, and I think it's completely doable with the hardware you guys showing there, and it'd be a fun project to do.
It would.